So what we're going to look at today, we're going to take a look at exponential functions. I think we might have time for simple interest. We'll see. But when you're talking about exponential functions, what we're talking about is a type of growth. So what we have is linear growth. And we've seen that already. So for linear growth, something, say, could be increasing like this. But for exponential growth, we're going to see something like this. You only grow so much as you move along the x-axis with linear growth compared to exponential growth. And, excuse me, there's also things like exponential decay or decrease as well. But some idea of where this comes up in the real world, linear growth, think about it if you're earning an hourly wage. So every single hour, the amount of money you earn for that day increases by the same amount. So if you're making $10 an hour, every hour you get $10. So if you have an hourly wage, basically your wage, what you're paid per hour, is going to be the slope of this line. Exponential growth, where you're going to see this, you might see this, say, in the way bacteria grow. So I'll go through some numerical examples to kind of give an idea of this sort of linear versus exponential. But what we're going to do with bacteria, we'll do this for example, we're going to assume that bacteria, they spread by dividing in two. So for example, let's continue this comparison. So let's say you're earning an hourly wage. At the end of 1 hour, you've earned $10. At the end of 2 hours, you've earned a total of $20. And let's say I'll insert this. Suppose wage is $10 per hour. So you're getting $10 an hour. After 3 hours, $30. 4 hours, 40. And you get the idea. Throw another 6 hours in there. So it's constantly increasing by the same amount. Jump of $10, jump of $10, jump of $10, jump of 10, jump of 10. That's linear growth. Now let's say for this bacteria, let's suppose bacteria divide in 2 every hour. So let's say that it's kind of hard to see, but suppose the bacteria divide in 2 every hour. Now for this, I'm going to slip in a 0 hour. So at 0 hours, we have 1 bacteria. After 1 hour, well, this is going to split in 2. We have 2 bacteria. After 2 hours, so I'll keep track of how many we have. We have 1, we have 2. After 2 hours, each of these are going to split in 2. So we're going to have 4 bacteria. After 3 hours, each of these are going to split in 2. We have 8 bacteria. After 4 hours, each of these are going to split in 2. We have 16 bacteria. 5 hours, let's see here, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Again, each of these are going to split in 2. We have 32 bacteria. And finally, at the 6th hour, we have 64 bacteria. So this is the difference between exponential growth and linear growth. The difference between each hour for your wages is $10. Here the difference is 1, 2, 4, 8, 16, 32. So the difference between each step is getting bigger and bigger and bigger, while the difference here is staying the same. So it's just 2 types of growth that you'll see sort of in the outside world. And I want to try to understand both. Now, for linear, we typically describe things using y, or we'll use the function notation. We use f of x equals mx plus b. While for this one, the function we're going to use is f of x equals b to the x, for b greater than 0. So we got our two functions for describing this kind of growth. And you can get a little fancier with this one. You can multiply this one by a constant. Sometimes that'll happen. And we'll be dealing with some exponential functions that are going to be a little more fancier than this. So first off, just to kind of review exponents real quick. So for exponents, when we see something like, say, 5 squared, this means 5 times 5, or 25. Or 5 cubed equals 5 times 5 times 5, which is 125. Now, what's going to come up in this section, we're going to also see negative exponents. And there's a bit that we could go into where these come from, but we want to know how to interpret them. Oh, excuse me. So 5 to the negative 2, what this means is 1 over 5 to the 2. The negative just means we're going to flip things. So this will give us 1 over 5 times 5, or 1 over 25. 5 to negative 3. That's 1 over 5 to 3. 5 times 5 times 5, or 1 over 125. So the negative means it's going to flip. Now, likewise, if you have 1 over a negative, we're going to flip this. It's same thing for 1 over 5 to the negative 3. So you're going to see these types of exponents. And so just kind of knowing what they mean is going to be helpful. I'm using 5 as an example. But 5, you could have all kinds of different numbers. So questions about that? All right. So let's take a look at the functions f of x equals b to the x for b greater than 0. Now, what's going to happen? I'm going to give you a couple examples. You might wonder, why does b have to be greater than 0? Well, let's say we have b equal to 0. Well, in this case, f of x would be 0 to the x, which is just going to be 0 for x not equal to 0, which is not a terribly exciting function. And then it'll be undefined. X is equal to 0. So what's happening here? If you take 0 and you give it an exponent, like let's say it's 0 to the second power. Well, that's going to be 0 squared, or 0 times 0, which is just 0. Or if you did 0 to the third power, well, same thing. You'd also want to be careful for negative values of x. F of x is 0 equals 0 to the x is undefined. Also, for x less than 0, and let me give you some explanation. For this one here, 0 to the 0 is just undefined. And then for this one, let's say you have we have 0 to the negative 2. Well, that's going to be 1 over 0 squared, or 1 over 0, and division by 0 is undefined. So that's going to be another issue too. So we want to stay away from b being equal to 0. We can get 0 to the 0, and that's undefined. Or we can get 0 to a negative power, and that's also going to be undefined. And finally, when it is defined, you just have f of x is equal to 0, just 0. Kind of a lot of trouble to just have 0. So we stay away from 0. If we let b equal 1, f of x will be 1 to the x, and that's just going to be equal to 1. So it's, again, not a very exciting function. At least it doesn't have all the problems with b being equal to 0. Just not a lot going on here. Finally, if b is less than 0, what happens here is we could get an even root. For example, we'll say it's not a real number. I'll give you an example to illustrate what's going on here. But if we let, for example, b equal -2, and then we get -2, say f of 1/2, be -2 to the 1/2. And you can't take, this is what we mean by an even root. This means that the denominator is an even number. And when the denominator is an even number here, we can't do this. This is like taking the square root of -2. This is not real. So it's what's called a complex number, and that's a whole other conversation. That's a two-dimensional number that we're not going to deal with. But if you're wondering why b is greater than 0, this is sort of why. When b is equal to 0, you don't really get a very profound function, and then you get in all kinds of trouble if you have divisions by 0 or 0 to the 0. When b is equal to 1, I mean, you could do it. It's just not a very exciting function. Why not just let f of x equal 1? Why bother with this? Finally, if b is less than 0, for values of x like x equals 1/2, this is going to be a problem. An exponent of 1/2 is how you represent a square root. You can try it on your calculator. Try taking the square root of a negative number. Calculator usually doesn't like that unless it's in some special mode that lets you work with complex numbers. So this part isn't going to be important for the homework, but if you were just wondering why b has to be greater than 0, or why we tend to go with that, this is why. And oh, I guess I should say b not equal to 1 is usually the case, though you could actually make it work. But b equal to 1 is kind of a not exciting result. But you could do it, that'd be fine. So what are we actually going to do with this? Well, I mentioned that b equal to 1 is not very exciting, but 1 does play a significant role. We're going to look at values of b that are between 0 and 1, and values of b that are greater than 1. So let's start out with b greater than 1. And to do this, I'm going to use a test function. Now, this part is going to be relevant. Well, I mean, it's all relevant, but this one could come back on the homework. So, for example, let b equal 2. So this means f of x 2 to the x. Now, we want to come up with an idea of what this function looks like. So what we can do is we can do an f of x chart. So for this one, when x is -1, f of x will be 2 to the -1. And remember, with our negative, we flip it. So it's 1 over 2 to the 1. And 2 to the 1 is just 2. Try this out on your calculator, and you'll come up with just 2. Now, another one you can try on your calculator. When x is 0, well, any non-zero number that has 0 as an exponent is equal to 1. And again, your calculator will verify that. Finally, if x is 1, well, any number to the first power, just like here, will be equal to itself. So what we have is this. -1, we get a half. 0, we get a 1. 1, we get a 2. So if we graph this, this would be 1/2. So at -1 and 1/2, we have a point. 0 and 1, we have a point. And 1 and 2, we have a point. So connecting these together, we're going to get a function like that. So this will be your f of x is 2 to the x. Now, I mentioned that f of x, if it's equal to 1 to the x, well, 1 to any exponent is just going to be 1. So it's just sort of just a constant line going across there. But now let's take a look at, we looked at when b is equal to 2, so something bigger than 1. But let's look at between 0 and 1. Let's consider b between 0 and 1. So for example, let b be 1/2. So this means f of x is 1/2 to the x. So again, we're going to use those same numbers, -1, 0, and 1. So what's -1/2 to the -1? I'm sorry, 1/2 to the -1. Well, it's 1 over 1/2 to the 1. Remember, for those negatives, we're going to flip things. And then anything to the 1 power, well, that's just that anything number. So that's 1 over 1/2. And if you take your calculator, divide 1 by 1/2, you're going to get 2. So when x is -1, f of x is 2. Now for 0, 1/2 to the 0. Well, again, any number except for 0 that has 0 as an exponent, that's going to be 1. So we have 1. And then finally, we have 1/2 to the 1. Well, any number that has 1 as an exponent, it's just that number. So this will be 1/2. There's a 1/2. Now in this case, we have -1 for x. F of x is 2. So -1, the 2. Now we have 0 for x. We have 1 for f of x. We have 1 for x. We have 1/2 for f of x. So we're going to connect these points. And what we're going to get is something like this, barring artistic license. But this is how we get our 1/2 to the x. So it's going to turn out there's a pattern. And you're not going to see it just yet, but I'm going to just kind of give it to you. But this is what you're going to have. And these are the two versions we're going to use for this function. The version where b is greater than 0, like b could be 2 or 3 or 7. It's going to look like this. And it's going to pass through this point, 0, 1. The other version when b is between 0 and 1, say like 1/2, or 1/3, or 1/4, or 3/4, we're going to see something like this. And a key thing here, neither graph, it'll get very, very close to the x-axis, but neither graph will cross the x-axis. Now you can modify these graphs so you can kind of shift them around so they cross the x-axis, but we're going to consider these without modifications. If you just leave them like this is what you're going to get. So questions about that. And again, we're not going to worry about b = 1 or b = 0 or when b is less than 0 or b is a negative number. And b = 1 is not terribly exciting. B = 0 is not terribly exciting. Plus, you get some undefined values, or some undefined values is the big issue. And then for negative values of b, you end up taking these roots of negative numbers that, well, they don't give you real numbers anymore. You have to deal with two-dimensional numbers, and we're not going to deal with two-dimensional numbers today. But if if you're interested, please ask. It's interesting. So, all right. So a special kind of function, a version of this, you'll see. Let's take a look. Is what we call E. Now, E, and let me grab a calculator here. I want to get the value on this. E is like pi. It's a symbol for a number. And let's see here. I got an E on here somewhere. I know it. There it is. E is approximately and it goes on and on forever. So what happens with E is it's an irrational number. So that means the decimals that come after the decimal point, well, they sort of follow, there's no pattern to them. And so what this ultimately means is we can't represent E, we can't represent it as some kind of fraction. So this is what we call an irrational number. Where it comes from is this. If we take 1 plus 1 over n, and we give it an exponent of n, well, okay, and we let n get bigger, then we get the. So I'll do like maybe 4 of these just to kind of show you what's going on. But let's say we let n be 1. So if n is 1, we get 1 over 1, which will be 1 plus 1 to the 1, or 2 to the 1. It's 2. So let's let n be 1,000. let's see, that will be 1001 or 1,000 to the 1,000. Let's see, I might have to approximate that. So it's about 2.71692, and it goes a little bit up farther along. And then finally, if we choose n to be like 1,000,000, we'll just do 3. So this will be 1,000,001 over 1,000,000. What does that come out to roughly? And that's going to be, here we go, 2.71828. We'll just do dot, dot, dot. But already we're closing in on it. Let's see, I'll give you the next number. This is the one that's going to be different. 0, and then it keeps going. So we've got it. When n's 1,000,000, we get up to here, and then we get a 1, and this one it's a 0. But the idea is that as you choose bigger and bigger n's, make these larger and larger, you get closer and closer to this number. And this formula, it actually comes from a, well, you can actually see it with some of the formulas for, let's see, it's if you're counting interest, for example, calculating interest. This comes up, have you ever heard of calculating compound interest? Well, this will come up if you're doing what's called continuous interest. You'll get this situation where there's an n in your formula, and it's going to be growing and growing and growing. Anyway, so what we're talking about is this. F of x, e to the x, and this is called the natural exponential. Function. So we're going to do some examples where we calculate some of these. Oh, here, and let me give you the graph on this. Now, note that e is bigger than 1. It's 2.71. Oh, dear, I erased the number. But at least 2.71828. Still see a little shadow of it there. Well, 2.71828 and more digits. That's bigger than 1. So the graph for e is going to look like the graph what's going to look like the graph for an exponential function with a b bigger than 1. So we're going to have here point, again, always on 0, 1. Now, e to the 1 is just e. We'll have this. And then for negative 1, well, here, I'll do this properly. Let's do our f of x. So we have e to the minus 1. And if I calculate this on a calculator, it's approximately 0.37. So that's going to put it, so about a third here, so a little bit above a third. So we'll go right there. This will be e to the 0. Again, anything to the 0 that isn't 0 is 1. And then e to the 1, which is our e, and again, 2.71. If we connect our points. We're going to have something like that. So any questions about that? So let's take a look at some calculations with exponential functions. So I've talked a lot about theory. We probably won't have time to get into simple interest today, because I do want to go over some problems that are coming from the homework, and they can be a little confusing. So let's take a look at this. Let's say we have 2 to the x plus 1. Now, let's say we're asked to find g of 3. Well, what we're going to do, g of 3 means we're going to replace all the x's with 3. So g of 3 is going to be 2 to 3 plus 1. Now, we want to be careful here, because we think about PEMDAS, we're told to do exponents first. So it's very tempting to say, we need to do 2 to the 3rd power. But that's not what we're going to do here. With this, you can think of this as having little invisible parentheses around it. So that means we're going to take care of this first, turn this into a single number, and then we're going to do the exponent computation. So this is going to be 2 to the 4, and then 2 to the 4 is 2 times 2 times 2 times 2, 4 2s, or 16. So questions about that? So we might be posed with a different question. Let's say we're asked to find g of 0. Well, for g of 0, again, you're going to replace all the x zeros. So this will be 0 plus 1. Or 2 to the 1. And then any number with an exponent of 1, just going to be that number. You'll get 2. So let's say we have this. G of negative 4. We'll again replace all the x's with negative 4. And want to remember, when dealing with these negatives, we're going to flip it. That makes the negative go away. Now 2 to the third, 2 times 2 times 2. Or 1/8. So take a look at another one. G to the 0.5. So what happens here, again, replace all the x's with 0.5. Now for this one, what I'd recommend is this is where you want to break out your calculator. And we'll talk a little bit about this after this problem. You go 2, give it the exponent of 1.5. And that's going to come out to approximately 2.83. So questions about that? So one of the things we wanted to talk about when we calculate these exponents is we want to make sure that you know how to do this on your calculator. So let me show you how this works on mine. This might be a little tricky. All right, so you see my calculator. What you're going to do, for my calculator, for example, if I want 5 to the third power, I'm going to press the number 5. So there's my number 5. And then this little button up here that has an X with a little box on it, right at the tip of my finger here, I'm going to press that button, that X with the box. And then I'm going to type in, let's say I want to give it the power of 3. I'm going to press the 3. Now mine, I have to close the parenthesis. So there's my closing parenthesis. I'll press that. And then I've got my equal sign. I press that. And so you can see what the calculator's done. It's going to give you 5 to the third power is 125. It's 125.0000, but if you get rid of those unnecessary zeros, it's 125. So calculators, when we do the exponents on the calculators, there's different types. And so you'll see things, for example, for my calculator, I type the 5 button, and then this X with a box, then my number, say 3, and then I have to put a closing parenthesis because the calculator, and I don't actually have to put the closing parenthesis, but it's good practice to close your parentheses. So this will give me 5 to the third, or 125. Now, other calculators, you might have this. 5 xy, type in 3, and then you got to hit the equal sign. I'm missing an equal sign here, but you hit equals. And this will give you 5 to the third is 125. Another way you can see this on a calculator, I think the TI calculators this tends to be a favorite of those. You have this caret symbol. And you have your 3. If you hit your equal sign or enter, I'll give you the 125. So depending on what kind of calculator you have, you can enter exponents different ways. Another thing too, if you're working with negative exponents, you don't want to worry about flipping things. You can do this with negatives also. I could do like, if I have 5 to the negative 3, I could go 5, this button, my negative sign, my 3, parenthesis, hit the equal sign. This one, 5, XY, negative sign, 3, hit the equal sign. 5, caret, negative sign, 3, hit the equal sign, and it'll take care of all this. If you use the calculator with your negative exponents, there's a good chance you'll get a decimal answer instead of a fraction answer, just for what it's worth, letting you know. But they're a little introduction to calculator usage on these things. Now for E, let's say we have this. Let's do a function with E in it. Look at these. We have something like this. Well, let's say we have X equal to 1. So f of 1. So what that means, f of 1 will be e to the 1 over 2 plus 1. And if you add your fractions, you'll get e to the 3/2 or e to the 1.5. I'm going to do 3/2 instead. And this one I'd recommend using a calculator. They're going to want you to use one. So E hides at different places depending on your calculator. So on mine, take a look here, see if you can see it. This times 10 to the X button, you can see a pi symbol in gold and a little E symbol in red. And so for me to get to that E symbol, I have to first hit this alpha button at the tip of my finger here. So I'm going to hit alpha, then I come back down to that times 10 with that red E. So I'm in alpha mode or red mode. I hit that, and then you have an E there. So if I want to do something with this E, like I want to give it an exponent, then I got to use my Xbox. So there's my Xbox there. So I'm going to press that Xbox button, and then you can see it. It's waiting. So to do 3/2, there's my 3. I'll type the 3. For divide, I'll divide. Divide and fraction bar are going to mean the same thing. And then I need to press a 2. There's a 2. And then I need to, for my calculator, I'm going to close my parenthesis. Just a good habit to have. And there you go. So, oh dear, I got a 9 in there. I'm sorry. Just to show you that I'm doing it, I'm deleting that 9. So now if I hit equal, take a look at what that's going to be. There we go. So they'll have you round these, and typically, let's see, 10,000. So this will approximately, this is 4.48168. 9 goes on and on and on. Tenths, hundredths, thousandths, 10,000ths. 5 or greater, so that means this bumps up to a 7. The rest of the digits go. Tenths, hundredths, 10,000ths, got it. So that's going to be our answer. So questions about that? All right. So let's see, there's one more application here. Okay, let me do one more example with this. We'll skip parts B and C. They're basically the same thing. Well, here, we'll do a B. Let's do a B. No sense in putting A, we're not going to do a B.
The last one went to, it was the tenths, hundreds, thousands, 10,000s. Is that what you said?
Correct. Tenths, hundreds, thousands, 10,000s. And then 100,000s and millions.
And it ended on, did you round up so that it was like 1.7 or was it 1.6?
It was 1.7. Let me see,
Okay,
I can bring up my answer again. It's 4.417. Or 4 and 4,817 10,000s. So let's take a look at a -7 here. So this will be E with a -7/2 plus 1. And I'm going to dispense with fractions. Let's just say it's E. This is -3.5 plus 1. And this will be E. We take care of this first, -2.5. And if I put that into my calculator, I'm not going to worry about flipping it. I'm just going to put this negative exponent into the calculator. I do my alpha to get E, my X box, -2.5, close my parenthesis, and I get approximately and to the 10,000s, tenths, hundreds, thousands, 10,000s. So I look to the number behind, it's 5 or greater. It's going to bump this up to a 1. And that's going to be my answer. So I mentioned that E comes from its equations that deal with interest rates. And what we can do with that, and we're going to get into this a lot in chapter 11, which is kind of an interesting name for them to give that. But anyway, moving on, no pun intended, I think. We're going to look at interest. Now we got to be a little careful with this interest formula. Let me double check something here. The reason is when you're dealing with days, they tend to treat the days in a year. In this section, they're going to use 365. But when you get to the next chapter, 11, we're going to switch over to 360 per year. And there's sort of some tradition behind why that is. But in this section, let me double check. Yes, we are using 365. So that's going to be a little sort of bump in the road as we move along. So 10.5, if we're talking about days, we're thinking days in a year, 365. If we're talking about days in a year in the next chapter, we're going to be looking at 360. All right, so we have a formula like this. So what we're going to do is T would be time in years. R is going to be your interest rate. P is what we call principal. Spelling on principal. I think it is PAL, like the person from school. That is how they have it. So double check that. The next one though is N. The next variable we're going to identify is N. Yeah, it is. And with N, you want to, N is going to tell us how many times we compound this. And so the way this works is the number of compounds per year. So when you deal with interest, let's say we typically talk about interest as an annual interest. It's how much you're going to pay or how much you're going to receive per year. We talk about annual interest. So exactly what is interest? Interest is sort of like rent on money. You can sort of think of it as if I let you borrow $1,000, well, I don't get to use that money, and so you kind of pay rent on it because you get to use it and I don't for that time period. Now you'll pay me the money back, and then you'll also pay the interest. So let's say you borrow it for a year, and I have an annual interest of 10%. That's kind of high. So what happens is when you come to the end of the year, you'll pay the $1,000 back, and then you'll also pay the interest, which is 10% of whatever you borrowed. Well, in this case, it'd be 10% of 1,000. Now, 10% of 1,000 is $100. So that means you'll pay me back the money you borrowed, the $1,000. You'll also pay back the interest, which is an additional $100. So at the end of the day, for letting you borrow $1,000 and me going without that 1,000 for a year, I'll get at the end of the year, not the end of the day, at the end of the year, $1,000 plus 100 more. So that's the idea of interest. Now, when you compound interest, what you do is you charge somebody that annual interest throughout the year. Now, does that mean I charge you 10%? Like, let's say I'm going to do this monthly. I'm going to compound the interest monthly. Does that mean that every month I charge you 10%? No, it isn't. What it means is I take the 10%, 12 months per year, divide the 10% by 12, and what does that come out to? Comes out to about 0.83%. So that means each month I charge you 0.83%. Why would I do this? Why not just wait till the end of the year and just charge you 10% instead of charging you 0.83% at the end of each month for 12 months? Well, the idea of compounding interest is the interest that, let's assume you don't pay the interest until the end of the year. So what happens to the interest that you owe at the end of each month? Well, what you might do is just let it go back into your debt. So what happens is that the next month I charge you that 0.83%. I'm going to be charging you on the money that you've borrowed plus that little bit of interest. And if you're not going to pay that interest off, it also goes back into the debt. So the debt's slowly growing and growing, and I get to charge interest, not just on the $1,000, but I also get to charge interest on the little bits of previous interest that weren't paid. And so the amount that owed grows and grows and grows. And so that's the idea of compounding. So let me talk about some terminology with this. Semi-annual. this is an N, equals 2. Quarterly, or 4 times a year, N is 4. Monthly, N is 12. Finally, daily, we got to be careful here. N is 365 or 360. And again, 365, what we're going to do in 10.5. 360, this is what we're going to do in chapter 11. So just to kind of keep in mind now, what's going on behind the scenes, like calculating the interest every month, you don't need to worry about that. But knowing how to identify your T, your R, your P, and then the correct N, and putting those into the equation, that's going to be important. So let's take a look here. Take a look at some of the homework problems. So let's suppose you deposit $2,500 in an account, earning $7.5% annual interest. So what's the value after 20 years? We need a little more information. Let's see here. We're going to do this. We'll assume compounded daily. It'll be compounded daily. So the trick to these problems is you want to identify the different parts of the formula. So first off, T. What is T? Well, T is in years, so T is going to be 20. Next is R. Now R, we want to be careful with R. We're given 7.5%. We want to turn our percent into a decimal. When we're working with this formula, R needs to be a decimal. So the way you do that, you take the decimal percent, move the decimal point 2 spots to the left. Finally, for P, the principal, that's how much you're going to deposit, $2,500. Finally, our N. And you want to think about how often this is compounded. And it's compounded daily. Now again, for this section, that means 365. Chapter 11, it's going to be 360. So we take our formula. We'll get 2,500. 0.075 divided by 365. Then we have 365 times 20. So we replace the T with the 20, the R with the 0.075, the P with the 2,500, in the end with 365. Now the trick to this is we want to turn this into a number and this into a single number before we try to compute any exponents. And we'll multiply this at the very end. So this will be 1 plus, let's see here. And then 365 times 20, so we'll have to squeeze that number in there. 7,300. There we go. So we then add 1 to this. And again, we're holding off on anything else until we get a number on the inside. And the exponent, that's a number. So now we're okay. We're good to go. We saved this for last. Won't do that yet. We're going to do the exponent now. So I'm going to use as many digits as I can. Xbox 7300. We'll get 2500. And what I'm also holding off on, I'm not rounding anything. I'm using as many digits as possible. There will be a time in the next chapter where we will do some rounding, sort of in the middle of the problem. But there's a sort of a special case for that. But for this, use as many digits as you can. So multiply by 2500. And this isn't bad. And with money, we're going to round to the nearest hundredth. That's going to be our answer. So what does this tell us? Well, if we have an account that pays back 7.75%, and we put $2,500, and we don't check on that account for like the next 20 years. Well, what I should say is we don't take any money out of it or put any in for the next 20 years. An account that's getting you 7.5%, that's probably something that might be involved in the stock market. You might want to be checking that. But let's say it generally 7.5%. Well, you put the money in, 2,500, let it sit there, don't take anything out, don't put anything in. And after 20 years, you'll have over $11,000. So not a bad deal for just letting money sit in an account and spend some time. Now, if you've noticed, though, this is compounded daily, and the percent is 0.75%. Now, we'll talk more about this when we get to the next chapter, but if you think about student loans, this hasn't changed. Student loans are also compounded daily, and it's not as high as 7.5% last I saw. I think the highest I've seen might be, gosh, I'm not going to remember this correctly, it was maybe somewhere between 3 and 5%, I thought. But the point is, if you have student loans, which are last I checked, were compounded daily, you can see how quickly that interest can make the debt grow if you don't pay it off. So if you borrow $2,500 for 20 years, well, let's play around with this. So doing a little extracurricular work here. Let's say 3.5%. I would enter in the entire expression into my calculator. It's going to let me type it in. So I'll make this 360 also, following the protocols of the next chapter. What will happen if we use 3.5% compounded daily for 20 years, and then using the 360, we're going to get a little over $5,000. So that means if you have student debt and you let it sit for 20 years and you don't pay any of it off at 3.5%, you would actually double your debt after 20 years. So just passing that on. We'll have some conversations about interest rates and so on when we get to that section. We'll see how quickly money grows when you invest, also how quickly debt can grow, which is something to keep an eye on. The interest rates are, just because it's like 3% or 2%, doesn't mean it won't have an impact over time. So let me do another one. And you're going to run into this. Let's say you invest from $2,000 at 1.2% annual interest, compounded daily for, so how long are we going to do this investment? Well, let's say we're going to do it for 100 days. So not even a full year. How much is in the account? So this is kind of an interesting one because we have to convert our time into years. We want to convert our time into years. So the way we can do that, take 100 days, and we have 1 year is 365 days. So we can use that conversion technique from before and make sure it's working. Our days should be canceling out. We should be left with a year. So this will give us 100 times 1 year over 365 over 100. Still have the year here. 365. Let's see if we do a decimal. Not sure if that's going to be a friendly decimal. Ooh, not very friendly. So I'm just going to leave it like this. I mean, you can reduce this if you want to, but we can call it 100 over 365 years. But we need to do this conversion from days to years. Oh, I want to reduce that. Let's see here. I don't think I can help myself. Top and bottom are divisible by 5. So if you divide top and bottom by 5, you'll get 20 over 73 years. So we get a fraction of a year is what we're actually getting. So that means for our time, be 20 over 73. So again, this is how much of a year we're working with. And then R as a decimal, 0.012. P is 2,000. And since we're compounding this daily, we're going to have n as 365. And again, just for this section. And there we go. So again, we're going to turn this into a number. We're going to turn that into a number. Let's see, bunch of zeros. And then for this one, let's see, 365 times 20 divided by 73. Oh, that's awful nice. Oh, no. We're going to get 100. All right. That makes sense. All right. It's going to be 100. Or 2,000. 1 100. And now we do the decimal or the exponent part. Using as many digits as I can. So this whole thing, Xbox 100. Again, using as many digits as I can. And then keep in mind, we only invested this money for 100 days, not even a full year. So we shouldn't be earning too much interest. Multiply by 2,000. Sure enough, we don't. $2,006. And then rounding to the nearest hundredth. And 59 cents. So any questions about that? Again, the major takeaway is we sometimes have to convert the time into years because it might not be given to us as years. It could be given as days or sometimes months. We just have to make that conversion. So that's going to be it for this section. If any questions, let me know. I kind of went into some things like with the different values of B, like B is 0, B is 1, B is negative. You don't need to worry about those for this section, but you do want to keep an eye on for B greater than 1 and B between 0 and 1. That you do want to watch. And well, there you go. So any questions, let me know. Other than that, have a wonderful weekend.
Is the